Hello, my name is Alberto Chichotko, student number G0037809. I'm a student at Grantham University, majoring in Electronics Engineering Technology. This is a video presentation to EE450 CAPSTONE Term 201204 with Professor Mohammed Maji Bigi. I apologize for mispronouncing the name. During the course of EE410 Technical Project Management, which was a precursor to this class, 3 projects were submitted with real-world implications for consideration. They were quickly discarded because they could not be tested and built to meet the requirements of 450. So I had to come up with another project suitable to meet the requirements for both. So let's take a look at what it was. Now that you see that my project is to take a ladder diagram control circuit for a washing machine and convert it or upgrade it to something similar to my Samsung washing machine, let's take a few moments to take a look at a few pictures detailing the various phases of the design and the build before I move on to the final product. Now that you've seen the various photos of different stages, here is the final build of the washing machine control circuits. Specifically modules 1, 2, and 3, which are the cycle option select, the safety module, and the power supply group. Originally it was supposed to be 8 modules, but it was beyond the capabilities of a one-person team to do all aspects of the entire project within the allotted time frame. As you can see, there's quite a few components here, actually 188 in total. One of the design aspects was to build this and limit electromechanical devices to 20% or less. Of the 188 components, 50 of them are integrated circuit chips, ICs, and 13 are electrical mechanical in nature. Those 13 are your selector switch, your push button switches, and the 2 relays. In effect, the end result is a 6% use of electrical mechanical components vice purely electronics, which is well below the established specification in the project. So one of the purposes of this was to provide functionality similar to a commercial washing machine with the appearance of being programmed. So when the circuit is turned on, and you'll notice the lights will come on, the main selector gives you various cycle options. You can select from normal, heavy duty, permanent press, delicate, rinse and spin only cycle options. And as I switch through each, you will notice the cycle indicators illuminate to the corresponding selection made. You may also notice that various LEDs on the board turn on and off depending on which cycle selected. That's because each cycle has predetermined defaults available. Now the user is able to select or deselect options as they want, just like you would your commercial washer. For example, in the normal cycle, the pre-wash indicator is off, but it is selectable. As you can see, as I depress the selector button for that option. Additionally, you can extend the rinse, and you can add an extra spin to it. Okay. The next series of lights deal with the load sizes, which can also be adjusted across the different ranges of medium, small, and low. Okay. You have other indicators, next group, which you can also cycle through, and these usually consist of your soil levels, ranging from high to low in various degrees. The next selection, I have to be careful here because this is a solderless board, so some of the components can come through. The next selection is for your spin option speed. As you can see, there are 5 indicators here, but only 4 are illuminated in the normal. That's because the no spin option is not available, so it cannot be selected. Okay, the final selection can also be programmed, which is the water temperature selections. Again, as you would any default. And as you'll notice, like right now, I will switch from normal to heavy duty. You will notice that any pre-selections that the user has entered for the normal disappear, and you're into the default configuration for heavy duty. Again, options can be selected or deselected as needed based on the user's preference. Details and defaults are specified in the project, and there are additional videos uploaded to this website, and I'll show a reference to that at the end, that you can take a look at that illustrates and captures the operational testing for each one of these functions to validate the specifications. A couple of things of interest that are easier to demonstrate here is the fault circuit. I've utilized 5 dip switches to simulate input signals from the other modules if I would have been able to develop them. One's being if the tray is open or closed. Once it's closed, a light will illuminate. If your door is closed, it will illuminate. That lets the user know that those options and safety features are enabled. I've incorporated an option that should you hit the start button with one of these open, for example, let's say the tray is open. If I were to hit the start button, I should get an alarm. Now, as a user, you get that alarm, and you would immediately do what? Well, let's take a look. We're going to close the tray door, as indicated by the light, and the alarm goes off. Then the user can go ahead and hit the start button, and the washing machine will start. There's extra features here indicated, whereas if at this point you start it up and the door happens to be locked, you go into an immediate alarm condition. A demonstration of that immediate shutdown function. Assuming everything is in order, and we will go ahead and turn everything on. Assume that now your door is locked and your washing machine is running because the start button has been hit. Somewhere along the line, power goes out, everything comes back on, the washing machine senses something's wrong, it drains the water, unlocks the door, and then it will send a signal back to the unit to say, go ahead, I'm finished, shut me down. This then is that indication, and when I press that, you should see the entire circuit go off. Resetting everything back to normal, I hit the power on switch, and everything immediately comes back online under its all default conditions, ready for you to do your next load of wash. Okay. The additional features does have a display. There's a video that shows the shutdown time. 10 minutes was the target. Let's say you turn on the power, you're sitting here on default, something happens, you get called away. Well, what's going to automatically shut down the washing machine in case you don't come back? This section, if you take a look right here, has a 3-stage timer that takes a 60 Hertz signal and turns it into a clock. Basically, it will go through counting and count off, and at the 10-minute mark, when you reach that, it automatically shuts down the washing machine. That video is also on the website for you to take a look at under the operational testing. Best achieved result was 9 minutes 58.7 seconds. Some of the delays could be due to the fact that it was a manual start time and a manual stop time while simultaneously starting the control circuit and then waiting for it to shut down. One of the challenges of doing this project was having appropriate test equipment to test the various components and circuits as they were manufactured. I mean, I did not want to risk blowing up the IC components with an untested power supply. So, doing some research and salvaging some components, I was able to take an ATX computer power supply, only about 140 watts, and modify it by installing an extra switch, adding some posts, and internally removing some wires and recircuits with a load resistor, so that I now had a regulated 5-volt DC power supply that I could connect to the DC portions of my circuit and do all the testing that I needed to prior to connecting the alternating current required for the power supply. You will notice that the transformer is very large. Initial calculations, not knowing exactly how much current draw was a result of the ICs and all the components, and based on the simulations would have been fairly high. As it is right now, I plan for and installed a 1/2 amp fuse in the primary on the transformer, and maximum current draws only around 100 milliamps or so. Exact details are also documented in the operational test document. I also had to deal with issues like the relays not sitting properly in the PC board. This resulted into the creative mounting of the K2 relay onto another board and routing the wires so that I can achieve the contact that I needed in connectivity. I also needed to reduce what seemed to be EMI or RFI interference. At one point, if I brought my hand anywhere near this section of the circuit, I would initiate an immediate shutdown. Come to find out, after doing some research and dismantling some things, that the most probable cause was the use of the stranded wires versus solid. The very close contact and the peg holes most likely led to the strands underneath contacting energized portions of other rows, and as I moved my hand near it and the wires moved, I created input signals and spikes that the circuit understood as a shutdown signal and eventually cut everything out. Other challenge was the mounting of the S1 switch, which is the selector. When ordered, the pin configuration did not match the boards, so I had to mount and connect in a way not to damage it and to reduce the possibility of soldering. Of all the technical issues and problems encountered, there were a total of 21 documented issues. Of the 21, 20 were technical in nature, being that there was some issue with the simulation program, such as the simulation program would corrupt the files. Not knowing this, I ended up reworking various sections to no avail. Conferring with fellow engineers that I work with on a daily basis, discovered that the simulation package that was used was prone to this type of fault. And it's funny because this is an industry leading simulation package, yet it would do something like this. Another issue, had to rework a number of circuits because a number of the IC component footprints in the simulation package, while they worked, once you put the labels on them for the virtual breadboarding and design, it mislabeled 3 pins on 3 different types of chips. Well, naturally, when you wire those in, your circuit is not going to operate as designed in the real world. I was fortunate enough to discover that before powering up the unit, but it entailed major rework and rewiring to correct those, and then follow up with the drawing designs to make sure I had accurate information. Other issues eventually ended up being critical when, while working on the last design, I did use a voltage regulator, a higher capacity voltage regulator that I inadvertently grounded while I was doing the operational test, and that resulted in the voltage regulator and the rectifier being destroyed. Doing quick replacement and research for locally available part ended up yielding a better voltage regulator that had a higher tolerance for input voltages and a suitable replacement for the rectifier, and as you can see, everything worked fine and I was able to meet the end results. Some of the lessons learned in this project is one person can't do it all. As a one-person team, I was responsible for the project management, the documentation, the design, the testing, and the building of the entire project. Being a full-time military member, those duties take precedence over anything else secondary, so it became very hectic and stressful to manage that, yet be able to come home and be able to work on this within a reasonable time frame. Many an evening where my estimated hours may have been 4 to 5, I ended up putting in a full 8-hour evening on top of a full work day just to be able to meet the requirements and minimum requirements for this course. Collaboration also with other students or other team members would have been beneficial. One person can come up with a very good idea, but one person doesn't usually come up with a great idea. Through collaboration and fellow teammates, you can always expand or modify an idea that ends up being better later on. When you run into issues or problems, someone usually has expertise or knowledge that can help you resolve that problem in less time. Most of my problem issues were resolved via internet research, looking into all my past textbooks, and falling back on my 30 years of electrical experience working in the military with power production that helped me get through some of these. And I do have to give credit where credit is due. My wife was also one of a key person that kept me going, whether it was helping me trace the circuits. She helped me wire this entire board over a period of 1 week just by simply calling out the pin numbers that I needed to make connections to. That and maintaining a steady supply of caffeine was also a key driving factor. The other big thing is, again, I keep going back to this, is simulation software. The actual brand name that I utilized was provided by Grantham University, but that's in the documents that the professor can submit for reconsideration for them to take a look at. But the simulation package itself introduced quite a number of problems that created rework or caused me to go back and question the validity of my design. It's great if you know how it's supposed to work or how your selected components do work, but when you don't know, you assume that the simulation package is correct. Many a times it was not, and after some great deal of head scratching and frustration and extra research, was able to determine what was the problem. Eventually went back to my original design and pressed forward to fix those. As I mentioned briefly before, some of the improvements that could possibly be incorporated into this package again is the reduction in the size of the transformer. Again, very large, even though it can be mounted on a PC, is definitely overkill for this section. The rectifier is rated for 4 amps. The maximum recorded amperage, even with a shutdown circuit, was along the lines of 196 milliamps. So that could be desized if need be. Depends on the cost factor. Either the difference between a smaller size chip and this one was a mere 3 to 4 cents, so keeping quality might be important. Additional factors to consider for improvements would be replacing the 60 Hertz signal with a crystal generated timing circuit. That way you would not rely on your household 60 hertz as your reference time for it. In this case, the fault with that would be if your frequency varies too much, then your time will also vary accordingly. With a signal generated by a crystal, it is not reliant on your input voltage or frequency, and in fact could be employed and installed in any device regardless of whether it is here in the United States or another country that uses different power source and a different frequency. The next thing that we will talk about is the schedule and the cost performance. Now I need to refer to some of my documents because it's quite a bit. The initial assessment done back in EE410, the technical project management portion, when I thought this up, I ended up with a schedule of approximately 180 days for both courses, which includes a 70-day period there break between the classes. Eventually I was able to complete the project in 209 days. This was only about 29 days over schedule. Original cost estimates with labor, training, overhead, equipment, material costs, I came up with 3 different values. One being an estimate based on a 0 rough order of magnitude variance, and that came up to a figure of about $57,400. My best case scenario included a rough order of magnitude variance of minus 25%. So on the low end, the project would have cost approximately $43,900. Now in the worst case, I added a variance of 25%. That would have then propelled the cost to approximately $70,857. After tabulating all the labor hours, assuming a labor hour rate with overhead of $80.50 an hour, calculating training materials, which is basically the cost of the 2 courses, capitalizing on the equipment that was used based on the guidelines, and actually spending $504 in materials to build this, the final project cost for the 3 modules came to $66,500. While over schedule and definitely over budget when related to the best case and the 0 variance expectations, I did come in under budget under the worst case scenario. So based on all these figures, the functionality of the circuit, meeting the specifications that I could, being an input from your house of 115 volts plus or minus 10% in amplitude, I was able to operate in a household ambient environment. I could not control other factors to test it down to the required 32 degrees or higher than 82. But I feel very confident that it would work based on the component selection. All were spec'd out by the manufacturer to be able to operate within those realms. I'm very confident that this project could further be developed to include the other 8 components. Well, I hope you enjoyed my presentation. This is again the washing machine control circuit for EE450 CAPSTONE for Alberto Chachutko, student number Thank you very much.